secret goal of this talk is twofold. First, I would like you to leave this room in an hour with a vague idea of what an operad is. So, I hope so. So this is, say quiet, okay, I can give definitions, no. But, sorry? Oh no, you're very clever. So for you, you will have a full idea of what an operad is. If the talk is good enough and if you add enough coffee during the break, maybe you'll have a very precise definition of an operad in your mind, say in an hour. And the other secret goal of the talk is to sketch the relationships with the, okay, I wanted to say some of the topics that we are going to try to understand and discuss during these 4 interesting months. That is multiple zeta values, Grothendieck-Teichmüller group, and of course deformation theory. So I will try to give you, and this will be very sketchy, so I apologize in advance, these new results in that direction, relating Operads with Grothendieck-Lie algebras, Grothendieck group, and whatsoever. Okay, so let's begin slowly. So the idea of the talk is, of course, to say what an operad is. And let me begin with, say, definitions. Okay, so it all begins with representation theory. So let me recall what kind of ideas we have here. Okay, so what is representation? Sorry? Which representation theory? Okay, here I take an associative algebra A. So I want to consider, say, an associative algebra. Right. And I take any vector space. I try to use almost all your notations. So let me take any vector space. Right, V. And what we can look at? We can look at the possible actions on A on V. So what does it mean? It means that we are looking for associative algebra maps from the associative algebra we have on the left-hand side and the obvious associative algebra we have on the right-hand side. So what is if I use the notation of the previous talk, we have mu is the binary product on A, which is associative, and on the right-hand side, what's the associative product? Is the usual composition of operations, okay? So this is classical representation theory. And this is a morphism of algebra. Okay. So the way I want to view this is as follows. It is, and let me show it in one example, is that we would like to model in one mathematical object, namely a certain associative algebra, some universal structure on any V, okay? So for instance, there is an object we saw in the previous talk, is a chain complex, a differential, okay? So what is a differential? It's a square zero operator acting on any V, okay? So how, and this is very general, and we can have this kind of algebraic structure on any V. How can we model this once and for all in just one algebra? That's quite easy. So what you consider is, you consider the algebra D, which is the free algebra in one generator. Let me call it delta, okay? So then if you look at the morphism of algebra from this guy to that guy, it's completely characterized by the image of the generator, okay? So let me do the theorem. So a representation of D module, no, let's say representation of D. So it's equivalent to what? So it's equivalent to an element rho delta acting on V. Okay, so far I'm right. So do I need to say more about this? This is the free algebra, so this is a tensor module on delta, and the product is given by the concatenations of elements. Okay. And then you want to encode the relations that guy satisfies. So if, for instance, I want to require that this squares to 0, okay, I will put this relation in the ideal that I have here. So, okay, now what we have is we put delta square in the ideal, and then you have this result. I don't want to call that a theorem. So this is the algebra of dual numbers. Okay, so this is the idea. The idea is once and for all to encode algebraic structure in one element, one well-defined mathematical object. And then when we want to prove some, say, universal results about the shape of the operations acting here, what we have to do is, no, just prove a simple result on that level. Okay, so let me give you another example, a bit more involved. Okay, so I said you want to prove some kind of relations on acting on some space. We have such an example in algebraic topology. So let me take a topological space X, okay, and so any topological space X, and what you can take for V, you can take the singular cohomology of X, right? So for instance, modulo 2, okay. So we might want to, here we have the space of all all linear operation acting on V. So here we'd have Ohm from V to V, and Steenrod constructed very natural operations acting on any of these guys. Wow, but you know the Steenrod operations, you have infinitely many such operations, okay? And then you check the relations, and well, it's quite involved, it's these Adem relations. So the idea is, instead of writing this for any element acting on element, what you do is, no, you just define one algebra. So you define, say, the Steenrod algebra, and the Steenrod algebra is the free algebra on some generators, so the Steenrod squares, etc. And you mode out by an ideal, and this ideal is completely generated by the Adem relations. Okay? Okay, and so Steenrod's constructions give you, for any topological space, such a map. They tell you these are, say, formal operations, and these Steenrod constructions gives you explicit action on any V, where V is this. Okay? So this is nice, and it's a nice way to work and prove universal properties for Steenrod operations acting on any space. But you see somehow not the failure, but the limit of this is here. This is only modeling operations with one input and one output. Okay? So what about if we want to do the same thing? Because in the previous talk we saw operations with two inputs. So what if we want to do the same thing with many inputs? So multilinear, let us go in the direction of multilinear representation theory. Representation. Okay. So this is a new world. What do we, if I want to have this picture, what should I put on the right-hand side? What is the space of all multilinear operation acting on V? Here, what I have to consider is I have to take this space of all maps. Okay? So this is exactly the space that we saw before that was composing the Orchid cochain complex. But here I don't want to, not yet. So at the end of the talk I will try to relate it with the Orchid cochain. But so far it's just space of all multilinear operations acting on V. Okay? So let me give that a name because I will use it very often. And a V. Okay. So if I want to have the same picture, I should try to coin a certain notion on the left-hand side, which should, now, such an element should be made up of formal operations with some relations. And this is what I want to define precisely. And then, having a morphism will tell me how these operations act here. That's my goal, okay? So if you want to do that, what you do is you look at this guy, at this paradigm. So this is the toy model for this theory. So let me try, in 2 or 5 minutes, let me try to extract the algebraic structure this guy satisfies, and I will make it into a definition. Okay. So this is made up of a collection of vector spaces labeled by n. Okay, so that's the first data, first piece of the data. So first, we have a collection of vector spaces. Okay. Indexed by n. Oh. And do these vector spaces carry some algebraic structure? Yes, we saw that just before. Is that now we have composition maps. You know how to compose operations. That I'm not saying anything new, it's just that. So we have composition maps. No. You chose to use the circle I. Of course, I will choose another one. They are equivalent. I will say something later. So here, the composition map. Okay, I could use the one before, and it would be a honest definition of the guy I want to use later on. That is, you give me two elements here, and I plug it at the highest place. We can do something else. We can iterate the circle I. So if you give me first an operation with k inputs. Okay, and then you give me k operations. Okay, what can we do with that? So let me try to use the same notation as in the previous talk. But the way I like to view this is that here we have an operation f with k input, so that's just a corolla. We have inputs and one output. Okay, and then we have, oh, I should be more modest and just do this. Okay, so G1, G2, and say G3. Okay, and what can we do with that? So of course we can put f, and the first input of f would be G1, the second input would be G2, and the last input will be Gk. If I write that picture, this amounts to putting my first operation below. Okay, it's the first level of operation. And then here I have a second level of operation where I put G1, G2, G3. Okay. This is the kind of composite of composition map that I want to consider. Okay. So of course this lives where? This lives in home. V times n is to V for n, which is equal to I1 plus Ik, the sum of the arity of these operations here. Okay. So this is the composition maps, and what do they satisfy? Well, they satisfy a certain associativity relation, because I can consider three levels of operations, and I mean if you compose multilinear maps, if you compose the first two levels and then the third level, it's the same result as composing these two bottom levels and then the top level. Let me write it. So this composition map is associative. Okay, so if I depict it, it's something like that. Okay, so I can first compose these guys. They give me operations, and in the end I compose these two levels, and this has to be equal to. So I leave you see, this is simple, I think, trees. I leave you to write this with f, g's, h, and if you want, with variables here, okay? And in the end you add the signs. Oh no, here there's no sign. Oh, see, yeah, there is a sign, but okay. I don't want to talk about this. Okay, so let me now write. Okay. but I think this picture is far enough to understand what is going on here. Okay, so you can compose this operation here. You get one operation with two inputs and one output, and then you compose, with 5 inputs. This one has 2, this one has 5. Thank you. And then you compose it. This is the associativity relation. Okay, and then, well, you have a very canonical element in RET1, is the identity of V. Okay, so this composition map, we call it gamma, is unital. Sure, because you have the identity of V sitting inside home VV, okay, and if you plug the identity here on the first level, on the second level, the composite is exactly the guy you started with. So what does this identity satisfy? Well, if you take an element F and you compose with the identity, okay, this is of course, so gamma of this is of course F, and then gamma of, if you take a certain G here and you put, let me put G here, and F there. Okay. And here you put the identity everywhere. Sure, you get F. Okay, so this is very simple, okay, but this is the kind of algebraic structure we have on the right-hand side, okay? So now, the type of algebraic guy I want to define it should have this kind of structure. So let me just erase the word paradigm and put general definition instead. So definition, okay, an operad is, we need a collection of vector spaces. So if I'm looking at an operad that I call P, I need a collection of vector spaces labeled by n. I want to view this collection as, for n, in RETN, a space of formal operations of RETN. If it is big, I have a lot of such formal operations, okay? So what do you want to do with this? So you want this to model some formal operations, but you want to be able to compose them. So then you do exactly the same thing here. That is, if you give me an element which lives in Pk, you give me an element which lives in Pi1, etc. Pik, I want to have a map, gamma, which tells me how these formal operations, how do they concretely compose. Okay? Well, I can keep this notation, and this is a formal picture. Okay? If I want to see the elements of Pk as corollas, labeled corollas with the vertex labeled by F, it is this. And then, so exercise, if you write precisely in terms of F, G, and H what this means, well, this collection equipped with this composition, they have to satisfy this associativity condition. And then what does it mean for it to be unital? It means that you should have a favorite element I in RET1 which satisfies exactly this, okay? That is, these composition maps, if you use this formal identity, you do not change the guy you put here, and same below. Maybe I should do that. Okay. You get F dot. That's an operad. So if you were afraid by that notion before, I hope you're not anymore. Well, so now since there are a lot of experts of operads in this room, and I know this, no, this is not, okay. Here so far is what people call a non-symmetric operad. I will tell you why in a few minutes. So far, this cannot model the symmetry of the operations I have on the right-hand side. I will do that in a few minutes. But before to do that, I would like to give you a few examples. Okay. If you have any questions, feel very free to interrupt me. Just So far, it's not that hard. I will go faster later. Okay, example. So the easiest say, the first example, it's example 0. So example 0 is, if you start from an associative algebra A with a binary product mu and an identity, okay? Well, I can view these elements, that's exactly what was here. Elements of A, we're formally modeling operations with one input. So let me cook an operad out of an associative algebra. What do? To A, you associate. Let me define P1 to be exactly A. Let me define Pn to be equal to 0 when n is different from 1. Okay, so this is the collection. Now you have only trees with one input and one output. So what kind of composition maps can you have? You can put only one guys here with one input and one guy on the right hand side with one input. So you need gamma, which eats two elements from A and produces one in A. Well, you basically take gamma P to be the binary product of your operad. Okay, and the identity is the identity. So what I am just saying here is that an associative algebra is a very particular kind of operad. In the other way around, any operad concentrated in arity1 is an associative algebra. So operads are a very natural generalization of the notion of associative algebra. Okay. So maybe you want a more fancy example. Okay. Let me just consider an operad that I call as for a certain reason. So as of n is what? I need to tell you what I put for formal operation in arity n. So let me decide that this is just one-dimensional, okay? So this is k of an element, mu n. So mu n, you can view it as a corolla with n inputs, okay? This for any n greater than 1, and choose it to be 0 for n which is equal to 0, okay? I take this collection, one-dimensional vector space in arity 1, 2, blah, blah, blah. Bon. This is not the full data of an operad. The full data of an operad, I need to define a composition. I need to define composition maps. So, what can you do? Now, what do we have? We need to define such a map. So what can we say? We can just define it to be, well, if you give me mu k, you give me mu I1, mu ik, then I have to tell you what is the image. Well, let us decide that this is just mu n. Okay? It's easy to check that this is associative. I mean, the result is always the corresponding mu. So if you do that and that, they're the same. And is that guy unital? Yes, sure. With this definition, mu1 is the unit. Okay? So this is definitely associative. This is definitely a unit for that composite. Wow, so that's, you have your first example of a non-trivial, say, non-symmetric operad.
So you don't take just any vector space of dimension 1, you take actually the field so that 1 goes to 1, right?
Yes, yes, yes. Okay. Okay, so here is the definition, here is an example. So we did that, so that we want now to consider representations of operad. So definitely.
The first example should be the paradigmatic.
It was obviously, yes, sure.
It should come before.
So example -1, no, example 1/2, sure. No, but you're right, it was so obvious that. It was modeled after that. Yes. Okay, so now we considered representation of algebras, we can consider representation of operads, and this is a p-algebra. So a p-algebra structure on a vector space V.
That's what I was asking.
Of course, on a vector space V is a morphism of operads, well, this kind of thing, to the endomorphism operad. Okay, so I did not define the notion of morphism of operad. That's easy. You have two collections, so you need to have linear maps from Pn to this guy in arity n, and these maps should obviously commute with the composite map. So that's not difficult. It's unit to unit, yeah. Exactly. Okay. So now we can say what do these formal operations do they encode? Okay, I defined an operad. So let us do this exercise. So it's example or exercise, so example 1 or exercise 1. Okay. So what is an AS algebra? Why did I choose these two letters AS? Okay. So okay, on the left-hand side, we have AS. Okay, and on the right-hand side, we have ohms from V to V. So first in arity 1. In arity 1, we have mu1, but mu1 is the unit. So in arity 1, does not help much. We need to send mu1 to the identity of V. In arity 2, we have one element, so we send it on the right-hand side. Okay, let me denote it mu, and this produces a linear map from V times 2 to V. What about in arity 3? Okay. So, do the guy in arity 3 produces one more data, or no, actually it will encode some relation. And let me do the exercise. Okay, so what is going on in arity 3? Okay, so there are two ways to get mu3. You can first, so on the left-hand side, you can consider this composite. Okay? So this is what? This is mu2, and the identity. Okay? I am in AS here. And then you can send that in the endomorphism guy. So this is sent to mu, identity of V, and then mu. Okay, but I can compose it. So if I compose this, I get mu2, mu1, and this is exactly my mu3. Okay, and mu3 is sent to something which should be the image of that. So what is the image of that? So this is gamma inside AS, and now I do gamma inside the endomorphism of V. And what do you get? Well, you get the composite of your honest maps. So this is just the operation mu of. Okay. So I didn't give you the definition of a morphism of operad, but I applied it. So you know what it is. And let me do it in the other way around. Let me put the mu in the other and on the right. Okay, under the composition map of AS, it gives the mu3. But if we look at the image in the endomorphism operad, what do we have? We have this composite. Okay, and now if we compose it here inside the endomorphism operad, we have the right composite with mu. And since these two guys in the operad AS, they get composed into that unique element, here these two elements have to be equal. Okay. So what is proved so far is if you have an AS algebra, you get an AS algebra, a representation of the operad AS. So far, you get a binary product which is associative. Okay? A claim then, if you check the image of the further element, they bring no new relations. So I claim that the end of the exercise is an AS algebra is precisely an associative algebra structure on V. So you see, we were able to model this first category, the category of associative algebra, with a new mathematical object. It's an operad. And this operad is made up of these formal operations. So you start with mu, okay, and then you can iterate that mu, but you impose in your operad this equals to that. And then what does it generate? Oh, it generates one formal operation per arity. For sure. If you give me a generic associative algebra and you ask me the question, how many operations can I cook with n variables? It's just one. So, great.
Not permuting.
Sorry?
Without permuting.
I said nothing. Exactly. So somehow this result amounts to saying something else, and I will unveil that later on, is that, you see, you saw at the very beginning that the algebra I considered, the algebra of dual numbers, was generated by one element with some relations. So I cannot make it precise right now, but I hope you will understand the meaning is that this proves a similar result. I gave the operad AS with all the elements, but this proves that AS has a certain presentation. The operad AS is the free operad on one binary generator. And the goal is to make this precise. I will do it. And then this operad, we take free operad on one binary generator, and we should consider some kind of operadic ideal, whatever the definition is. And here what we put is the associativity relation. So operad should admit some presentation with generators and relations. Okay. So, I mean, if you don't know what a theorem should be on the operad level, think, what should that theorem be for an associative algebra? Nearly all the time you know what it is, and then, okay, it works exactly in the same way for operads, mutatis mutandis. Okay. So this is, say, operad. So it was obvious that there was no symmetry group action here, so I would like to put into this picture the action of symmetry group, and maybe say that we can do operad outside the context of vector spaces. So let me do this right now. Okay. So let's say more general types of operads. So I would like to write a big capital O, operads. This stands for say generalized operads. This was the very first example, but I want to give more definition of that shape. First thing, exactly. So the first point is that if we look at home from V n to V, here by permuting the inputs of the operation, okay, I can permute the inputs using an element of the symmetry group with n letters. So this shows that this is a module over the group. So it's an SN action by permuting the inputs. Okay, so I should take the board I had before, take the definition of an operad, and adding this in the data of an operad. So now, what would be, okay, so this guy admits an action of the symmetry group, and this action is compatible with the composition in a certain way with the composition of operations. So this action is compatible with the composition maps. Okay, now you can make out of this example a general definition, and this will be an operad. So let me just say it. So an operad, so if you think of the previous definition and we upgrade it with the SN action, an operad is a collection of write SN modules equipped with composition maps which are compatible with this action. Okay? You will have all the details starting next week during the course, but I think it's fair enough. Okay, and this allows you to model symmetry of the operations, and I prefer to give you one example. So let me now consider the operad I had before. So let me give you one example. It's in the same spirit as us. Let me say com. So what will be com n? Again, you take the same definition. Maybe I will put a new n. So one-dimensional space for n greater than 2, and you take 0, oh sorry, n greater than 1, and 0 for n equals to 0. Okay? Okay, so this is a collection of vector spaces. I need to tell you what is the action of the symmetry group here. You take the trivial action. Okay? Then how do you define you define the composite map? You take exactly the same one, and since I completely cheated and I didn't tell you the explicit compatibility relation, you cannot check it here, okay? But trust me, this is...
Everything is invariant.
Yes. But to get the feeling of what this is, I think this is enough. And so you interpret nu1 as being the units. So this is an operad. This is an example of an operad. With a small o. Okay. Again, you copy-paste this. What is a P-algebra structure? It's a vector space equipped with a morphism of operads. So here, we really want these maps from Pn to home, Vn to V, to be equivariant with respect to the symmetry group action. If you ask this, then you get something more here, is that, okay, let me do the exercise. Okay, nu1 is sent to the identity of V. Okay, and now what about nu2? Nu2 gives you again a map with 2 inputs and 1 output, but be careful, this should commute with the action of the symmetry group. So since the action here is trivial, okay, the action here should be trivial. So this means that your mu is a commutative binary product now. Okay, and by exactly the same arguments, you prove that your nu is associative. So this operad, now the upshot of this exercise is that algebras over that operad are commutative associative algebras. Okay, so we have two first examples of categories of algebras which are nicely modeled by operads. Okay, so this is the beginning of the theory. Okay, so now let us try to look at more interesting examples, or complicated, or richer. I don't know how to say that. Okay, first we want to. Sure. The action which is trivial is on the operad. Here you have a full action on these guys. But if I want this map to be S2 Sn equivariant, the image of this element should, the action of S2 on this, on the image of this, should be itself. Here is the image which should be trivial, not the full home V times N to V, of course. Okay, so now here we come to, we can now that you have a vague idea of what an operad is, we can go to more involved examples. Okay. First, what did I use? I mean here, I used vector spaces, the category of vector spaces, okay? And I used the fact that I had a tensor product. But so what did I use here actually? I used a category with a monoidal product and the fact that this guy is symmetric. So you can do operad in over any symmetric monoidal category. Okay. And we have a lot of examples of symmetric monoidal categories. You can consider sets with a Cartesian product. You can consider differential graded modules with the tensor product, graded tensor product. You can consider topological spaces with the tensor product, simply show sets, Cartesian product. Yes. Yes. Yeah. And then and so on and so forth. Okay. So now, again, you copy-paste the definition I gave you. What is, say, a topological operad? A topological operad is a collection of topological spaces with an action of the symmetry group. If you give me elements of these topological spaces, you should have a way to compose them. And instead of giving you the definition, I prefer to give you again an example. If the endomorphism operad was the toy model of the story, this is the mother of topological operad. So, let me use a curly D. So what will be D? So I want to consider, so first, I need a topological space for any n. So what can be this? I want to consider configurations of disks inside the unit disks. Okay? You label them. So Dn is the collection of. Okay? Alors here n equals 3. Okay, so let me really put. Okay. So you take disk and you look at disk inside the unit disk. Okay?
So the coordinates are the center of the circle and the radius.
Yeah. And then, okay, so what is, so topological space, what is the action of the symmetry group? You just relabel the disks. Easy. Then you need a composition map for that. Okay, so of course this is called the little disk operator, obviously. What is the composition of this? Well, if you take, so you take one disk with say k inputs, let me just give an example with 2. And if you take k such configurations, so here let k to be 2. No. Okay. Okay. What can you do with that? You take this disk, you shrink it a little bit, and you put it at the first place, because this is at the first place here, and the second place, you shrink it, and you put it at that place. So the image and the gamma of these 3 guys gives you the configuration you had at the beginning. Then you have something like this. Okay, ooh. And then here you have 1, 2. Okay. And I claim that obviously this is associative. I mean,
relabel 3, 4 there.
Thank you. And you relabel. I hope you can read. Thank you. Okay, so this is a topological operad. Okay? The little disk operad. Okay. Now if you look at what we did before, a very natural question to ask is, what is an algebra of this over this operad? Sure. Okay. So an algebra over this operad. Well, first let me give you examples of algebras over this operad. So the end of the last talk was all about two-fold loop spaces, right? Okay, maybe we can consider that. So we can consider two-fold loop spaces on X. So these are continuous maps. These are continuous maps from D to. so the disk in dimension 2 to x, which sends the boundary to the base point of x. Okay, and I claim that the little disk Operad acts on any of such guys. Okay, how do you see that? So I claim that you have an action of this. This is an example of a D algebra. Okay, the construction is quite easy. So you start from a configuration like this. So this is an element of the Operad. And I say that you can view this as an operation acting on these guys. So here we have 2. This is an operation of variety 2. So it should act on 2 double loop spaces. So I need to have one map F from the disk to X. Okay. And I need to have another map, say J, which goes from the disk to X. Okay. And I claim that this operation can act on that to produce one new double loop space. How do you do that? What is the action of this guy on these two guys? Well, what can you do? You draw that again, okay? And you want to map from here to X, okay? The idea is to send the boundary and what is here. So you send all of that on the base point, okay? And here in that disk, you use F. And here in that disk, you use G. And it gives you a double loop space. Okay, great. Now, this is the easy part. I cannot do the other part because now there is a theorem which is, oh, and I want to use colors for this. So this is, say, the very first theorem on Operads. So it was proved by, say, Bormann, Vogt, and May.
Almost 50 years ago.
Yes, but we have new result in between. Is that if X is a connected space, okay, and X admits a D2 algebra, so X is a D algebra, if and only if, well, I would like to say that X is a double loop space, but since we're working in homotopy theory, we can't say is. It's homotopic to a double loop space. Okay. So roughly speaking, D algebras are up to homotopy double loop spaces. So that's the first result which motivated the introduction of Operad. That's the beginning of the Operad. 40 years ago. Okay. So I say this is the mother of Operads because now we have several nice results related to that Operad. And let me mention 3. Let me mention 3 of them. Okay, so the first result is the thesis of Fred Cohen in '76. Well, look, we can do Operads in any symmetric monoidal category. But if you have a monoidal functor from one category to another one, for instance, say like this, we take the homology over a field of characteristic 0, for instance, anyway. Since this guy is a monoidal functor, any topological Operad will induce graded Operads. Maybe should be graded vector spaces. Okay, so I can do that here. I can consider the homology of the little disk Operad. And this is a graded Operad. Wow, that's the Operad which models Gerstenhaber algebras. So this is really beautiful. This is the first result. But then, from that, and from what John explained before, you have this Deligne conjecture. Alors, the Deligne conjecture, Makler-Smith, Kontsevich-Zoll-Bellman, blah, 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 theorem. Okay, so actually, and it was not even a conjecture. It was a question by.
Deligne is always vague.
I didn't say it. Bon, so another way of saying the Deligne conjecture, I love very much Gerstenhaber algebra to homotopy, is you take the Hochschild cochain complex on an associative algebra, and Delling was asking, okay, on the homology level, we have a Gerstenhaber structure. Can we lift it? So that's what John said. Lift means to have a G infinity algebra here. But actually, Delling's question was formulated in terms of topological operads. So does this guy have an action? So has an action. This is very vague. Has an action of a topology of an operad equivalent. So, and this is where I'm vague, and I leave Ike to make it precise with cofibrant operads in topological spaces later tomorrow. Has an action of an operad equivalent to the chains of the little disk operad. Okay, and then you have to prove that G infinity, the operad of Gerstenhaber algebra up to homotopy, which is something which is homotopical algebra, is equivalent to that guy. And there you have Grothendieck-Teichmuller group here. I have no time for the proof, but then let me mention in red. Let me mention a result which really, another result which really motivated this program, which is a theorem by Benoît Fraisse. It's much more recent because it's 2012. So, okay. Here I will be very sketchy. You take the little disk operad, you take the irrational version of that, Malcev completion of it, whatever this is. Please ask no question. You want to look at the automorphism of that operad, so morphism of that operad, but up to homotopy. So you want to consider the homotopy automorphism of that operad. Again, I leave Ike to make that precise tomorrow. You take a cofibrant replacement of that guy, and you look at the automorphism of the cofibrant replacement. If you understand what this is, wow, you're great. Then Benoît proved that this is the pro-unipotent Grothendieck-Teichmuller group. Okay. So this is really one of the several results of these last years which really motivated this program. You see, we have operad for 40 years. We have this. Now I'm going to say more about this, the period during the 90s. So every 20 years we have nice theorem in operads. We have this one, result in the 90s that I want to sketch right now, and this result here. Okay. Wow. So I have say 5 or 10 more minutes. So now I should be very sketchy. I plan to talk about the operad, which is made up of the moduli spaces of curves. But let me skip that part, which is really beautiful. Let me go to, we said G infinity. So what is G infinity? And at the core of G infinity operad, there is causal duality theory. So I really want to spend the last 10 minutes saying a few things about causal duality theory. So what should I say? Let me maybe show you just one thing. I prepared several slides and I have no time to give all of them, but to motivate Ike's talk even further. Is this working? Wait. I want to show you why homotopy theory appears here, or in the other way around, why do we need? Why are operads so useful in encoding higher operations? I mean, by hands there are many things, I'm too stupid, I can't do it. But with operads, wow, sometimes we can describe a few things. Now, is it working? Not really.
Perhaps people in the back can move the shades on?
Yes, thank you. Yeah, perfect. Just I want to show you very basic things. It's on my homepage, so if it goes really too fast, first you interrupt me, and then you can go there. So, you see, if you take two vector spaces, and if they are isomorphic, you have an algebraic structure on, say, the left-hand side. What can you do? You transport the structure, and for instance, you have a binary product. Since you have an isomorphism, you define a binary product on the right-hand side, and it's again associative. So algebra behaves well with respect to isomorphism. What about homotopy? So do algebra mix well with homotopy theory? In homotopy theory, we do not necessarily have isomorphism. We have homotopy equivalences, okay? So for instance, a deformation retract, okay? So here it's a weaker notion. You see, the composite of P with I is not the identity of A, it's just homotopic to the identity of A. And this will somehow break the strict relations. And let me give you two simple examples. So let's say that on the left-hand side, I consider a very simple algebraic structure, a unary operator which squares to 0. Okay. What is the effect of transporting this guy from left to right? Well, I transport it. So how do you transport? You apply first I, you apply delta in A, and you come back. Let us iterate this guy. Does it square to 0? Well, if you compute it, in between you have pi, which is not equal to the identity. Okay, if it were, sure, then this is the identity and delta squares to 0, and you get the strict relation for this transferred delta. It's not the case. It is not. So you have new world which is appearing here. It's not 0, but still this transferred structure shares nice algebraic structure. So what can you do? Well, here there is a failure. This is not the identity. So let us consider this operation. I delta H, the homotopy, delta and P, okay? And then what can we say about delta 2, small delta 2 and small delta 1? Well, does small delta 1 square to 0? No, but it's the image of delta 2 under the boundary map. Okay, so delta 1 does not square to 0, but it squares to 0 up to homotopy. This relation does not hold, it holds up to homotopy. Wow! So, first transferred structure, first homotopy, do we get higher guys? Yes, actually you can continue this process, and here I'm cutting short, and you can introduce a full tower of operators, defined by that way, and they all satisfy this kind of relations. So, this is a way you relax the relation delta squares to 0 up to homotopy. So such a structure with all this tower of operators is often called a multi-complex in the literature. And of course, if you take a multi-complex structure where all these guys are 0, you recover the structure you had at the beginning. That's just an operator which squares to 0. Okay. So you see, we had an algebraic structure on the left-hand side. We were able to transfer it on the right-hand side. Forget this very long word. It's just, there is a theorem behind that. We are mathematicians, so I wanted to give a theorem. It's not just vague ideas. We can definitely relate these two. And this homotopy transfer theorem has many applications in literature. If you think at a bicomplex, this is exactly the structure I had at the beginning. Graded space, a differential, and another operator which squares to 0, okay? Let me take H to be the homology with respect to the first differentials. That's the E1 page of something. And on this E1 page, we have the transferred delta. And then we have higher guys. Well, we've seen that before. This is exactly a spectral sequence. So the structure that I described before is actually a lift of the spectral sequence associated to a bicomplex. Said in another way, this gives you another way to interpret spectral sequences. Spectral sequence is all about homotopy theory like this. And you can find this exactly in the papers on the first papers on cyclic homology. The way you prove that, you can prove that all the definitions of cyclic homology are the same, they rely on this theorem. Wow. Oh. Okay, let us pass from unary operators to multilinear operators. If we start from an associative product, okay? Okay, this is the way I like to draw the associativity relation. Let us do the same kind of things. We have an associative product on A. We have a space H which is homotopy equivalent, and let's try to transfer the structure. Okay, so you defined a new binary product on H by going from H to A, applying the multiplication in A, and coming back. Let me ask the same question. If we do that, is this guy associative? Okay, so this is the picture. Okay, in general, no. No, if you check, this transferred guy is not associative. So again, you introduce one new operation. Here it will have with H. And if you check, the boundary of this new guy gives you the associativity relation. So on the transferred structure, the associativity relation does not hold, it holds up to homotopy. Okay. Again, there is a full tower of higher homotopies that you define with sums of planar binary trees, and they satisfy this nice relation. And this is precisely the definition of an A-infinity algebra or associative algebra up to homotopy. Okay? So this is why I wanted to give you that example to show you why operads are good for. You can do that by hand. I mean, Stashev, he didn't know. No, in 63, he didn't know what an operad was, of course. See, this is the prehistory of operads. But nowadays, okay, this example you can do it by hand. Okay, good luck. But then if you want to say, you take the definition of a Gerstenhaber algebra, and you want to have the definition of a Gerstenhaber algebra up to homotopy. Good luck. Good luck if you want to do it by hand. Yes. Then this is why you need causal duality theory. Okay, so then you have this the same homotopy transfer theorem for A-infinity algebra, and it is related to two things that you know is these higher Massey products on singular cohomology. So I give you an example where it is used, these Borromean rings. It was also used to detect when a complex manifold has or not can have a Kähler manifold structure. But let me skip this. Okay, so the idea for that is that this is the picture that I will not explain the details, that you have a category of algebra. We're using an operad to model them, but very often this category of algebra does not have nice homotopy properties, okay? We saw that in the two previous examples. So the idea is to replace this operad by another operad. So here I'm in the context of differential graded operads. So you change the operad by another differential graded operad, which with a map from P infinity to P, which on the level of the chain complex is a quasi-iso. These are quasi-isomorphisms. And you want this guy to be, let's say, free, whatever that means. Okay. And then we know that algebras over that have nice homotopy properties. Okay. The way you do it is causal duality theory. So give me just 2 minutes. I want just to explain why is causal duality theory good, and to relate it to the topic of the program. You want to resolve this, and you see that if you resolve that by hand, you first, in that free algebra, you put a generator for that generator. You put that guy for that relation. This is for the relation of the relations, and these are the syzygies, the classical syzygies. You do exactly the same thing for operads. Okay, I will try to explain that next week. So what is causal duality theory is you have an operad that you want to resolve with a free operad. Alors, you can do this by hand, this consultate procedure. No. Bon, it can take a lot of time. Huh? The real good point with causal duality theory, it is going to produce for you, once and for all, under a universal algebraic property, a space of syzygies. Sometimes it's good, sometimes it's not, but quite often it's good. And the idea is as follows. Well, maybe I should skip the technical details. Okay, forget the tech. No, I have no time. I will do it next week. Just to tell you this, causal duality theory produces a candidate for these operadic syzygies. So the goal next week will be to explain you how we can do that. And of course, examples. All the guys we saw before, they are causal operads, so algebras are operad, so it's a good thing. Yes, and I would like to finish just with one word with relating this causal duality theory with the topic of the program, and I have just two results that I want to write in red. It's not a result, it's just that you keep in mind two ideas. First one.
Another color, because red is very difficult choice.
Okay, yellow, but I want them to be emphasized. So, yeah, but I want to emphasize the relationships with the. Okay, so causal duality theory was proved on the level of algebras by Predi in the 70s, and it was extended to operads by John and Ezra Getzler and Ginsburg Kapranov in the 90s. So in the 90s, you have your new nice, beautiful result on operads. Two things. How is this related to multiple zeta values? So, because I said nothing about multiple zeta values, the causal duality theory is very much related to the bar construction of algebras. So you have a construction which is the bar construction of algebras. Okay, and this bar construction, it's the co-free co-algebra on an algebra A. And since this is co-free, so you take the deconcatenation product, you can define you want to make this into Hopf algebra. So then you consider the shuffle product, and this is very much used in multiple zeta values. So let me just write this. Okay, and so this is a way to relate properties of Koszul algebras with multiple zeta values. And I don't know in which precise way, so I prefer just vaguely say this. And the other result that is very interesting is that how were these guys able to extend causal duality theory from algebras to Operads? This is a particular type of chain complex. Let me show you the differential here. The differential here is you take tensors of A. And you saw before that the way I wanted to think at elements of A were operations with one input and one output. What is the differential here? It's the unique co-derivation which extends the product. It means that each time you have two elements like this, you compose them. Okay, so this is a graph, labeled graph. And the differential is exactly given by the product of A. It's an vertex, it's an edge contraction. So this is a graph complex. Okay? The way you can extend causal duality theory for Operads is defining a bar construction on the Operad level. So what is the bar construction on the Operad level? You take trees and you label the vertices by elements of your Operad. Okay? And then, since you have a way to compose these operations, you can take any edge and then you contract this edge using the composition map of your Operad. And actually, this was defined in '93 by Koncevich. This is graph complex. Okay? And then, I think I read once, maybe in your paper or in Ginsburg-Kapranov's paper, that it's this paper who told them, wow, yeah, that's how we can define the bar construction for Operads, and then causal duality theory. So this leads to causal duality theory, but I want to give one theorem here, is that 2 years ago, there was a theorem by Thomas Willwacher, This graph complex can be very hard to compute, especially when you have, this is a tree, but when you have a graph with genus, it's very hard to compute. People who tried in this room can tell you that. Willwacher was able to prove the following theorem. He took some graph complex a la Koncevich, and he computed, and this graph complex acts on the deformation quantization of Poisson manifold. Okay, beautiful. And he computed H0, and he proved that H0 is the Grothendieck-Teichmüller-Lie algebra. Okay, so this is, say, the second theorem. I made a mistake? No. So this is, I think, the second theorem that really motivated us to propose this, to have this proposal for the program. So I shall stop here. But yes, say. No.
One theorem, because the theorem of Reserve follows just from Tamarkin proof of formality of little disc, so Willwacher result implies this immediately.
Alors,
one theorem.
I have to make two comments now. Well, Fraisse does not claim this. Fraisse claims that this result is the stable version of his result, and that his result, Fraisse claims that this implies that, but not the other way around. Don't ask me more. Yeah? He claims that this is a stable version of that.
Therefore,
okay.
Just from formality,
yes.
So essentially he computed, this is zeroth homology of the deformation complex.
Yes. Yes. Yeah.
Therefore, it just must act
yes.
on little bit. So this follows
by integration. Okay. I should mention something else related to your work, is that you proved that the pentagon relation implies the hexagon relation, and Willwacher has a second proof of that statement. So this is also very much related to... Sorry. Okay, my claim was not second thought. My claim was that this allows you to prove this statement. So this is also very much related to this kind of ideas. So I think it's very exciting for me at least, to understand how all these ideas are.
It's important
Yeah.
to emphasize. The proofs are completely different. This is homological algebra, this is algebraic. Not what he said.
Are there more questions?
You have a question? Okay.
So, thank you again.
Thank you.